Hello friends, welcome to today's lab session. So today we will be covering the next lab, which is your experiment number 6 in the syllabus copy. And the name of the code is, we'll be writing a Verilog code, for counter with given input clock and check whether it works as clock divider, performing division of clock by 2, 4, 8 and 16, and we'll also verify the functionality of the code. Okay, so it means what now friends? We'll be having a clock, we'll be having a main clock, and then using that main clock, we'll divide it into sub clocks. And the division amount must be what now? It must be by 2, 4, 8 and 16. That is, the given clock must be first divided by 2, then it must be divided by 4 and 8 and 16, so on. Okay. So this is what we'll be trying to do. So that means in order to illustrate this in more detail, I'll just show you one more small this thing. Okay. Yeah. Okay, so this is the thing. So you can observe here friends, this is what the whole logic we are going to apply in our whole code. If you can see here clearly, what we are trying to do is, this is my reference clock. This is my reference clock, which is of say t is equal to 2t. That is, the time period is 2 times small t. Okay. Then what we are going to do, we are going to divide it by 2 raised to n. Here n, initially we take it as 1. So it means what now? 2 raised to 1. That is, we are dividing this reference clock by 2. So when I divide this reference clock by 2, you can see here the time period is increasing. The time period is increasing, whereby thereby you can see that time, you already know that time and frequency are inversely proportional to one another. So you can observe clearly here, in one cycle, that is in one period, we have 2 cycles, but here we have only 1 pulse. We have only 1 pulse. That means what now? This whole 1 has been divided into here. That is, this whole 1 period has been divided into a single pulse. Or in other terms, you can say that we are increasing the time length. That is, say for example, if this is some 10, then we are multiplying this 10 by 2, thereby we are getting here what now? 20. You can remember like that. That means this could be again increased. Say for example, this n is equal to 2. That means what now? 2 raised to 2, which is 4. That means we will be dividing by 4. If you divide by 4 means what now? If this is 10, then it will, this pulse would be how much now? 10 into 4, which is 40. That's all. So that's what we are trying to do in our code. Whatever the experiment we have, first we will divide by 2. So the first waveform which we will be getting is of this one. By 2 is nothing but this thing. That is, we will be dividing, first we will be having a reference clock, then divide by 2 means what now? It will be again increasing by an amount of twice. That is, it's nothing but f is equal to 1 divided by 2t. So you can just remember this whole waveform. Based on this only, we will be deriving the rest of the clocks, which is divided by 4, 8 and 16. Okay. Now let us have a look at the code. So this is our code. So as usual, the time scale, we have kept it as, I hope so it is visible. The time scale, we have kept it as nanoseconds. You can change it to anything like picoseconds or microseconds. You already know how to do it. These all are comment sections. Going ahead, so this is my module. The name of the module is counter divider. Then we will be, the next thing is, we will be taking all your inputs and outputs. So how many outputs we have? First one, clock divided by 2. Next one, clock divided by 4, 8 and 16. Finally, you have 2 inputs, which is clock and reset. Okay. And so you can observe here, these are my outputs, clock divided by 2, 4, 8 and 16. And my inputs are what now? Your inbuilt clock, which acts as a reference clock, and the reset. So these 2 are my inputs. Okay. So as you already know, we will be using your behavioral description style of writing. So therefore, I need to use my 2 important keywords, which are resistor and always 8. So inside resistor, we will be defining our output. So you can see here, we need to initialize our output, which is 4 bits. So that's why I've taken here 3 down to 0. And the initial value of our count is 0. That is, all the bits are set to 0. Next, always at pose edge of the clock. Pose edge of the clock means what now? Always at the positive edge of the clock, we need to start doing our execution. So always at positive edge of the clock, we'll be starting our execution. And as you know, the reset is of two types. One is active high, or the other one is active low. Right now, we'll consider it as active high. That means if the reset is equal to 1, then the count is set to 0. Else, you will start with the counting. So that means what will happen now, friends? First, it will check whether the clock is at the rising edge. If it is at the positive edge, then it will check, is reset equal to 1? No. If reset, let us assume it is not equal to 1. If it is not equal to 1, then it will increase the count. That means initial value of our count is what now? 0. Then it will become +1. That is 0, 0, 1. And so on. Until when? Until your reset becomes equal to 1. So this is my one part of the logic which you have written. Next is what now, friends? We need to divide it. How to divide it? As you can see, our count has 4 bits. That means if I want only divide by 2, then I will be taking the LSB, which is count 0. Is that clear? I'll be just taking the LSB. And another very important thing, we need to write, we are writing here assign. You might have got a confusion that assign doesn't comes in behavioral description, it comes in data flow description. It can be used because we are using it outside your always. Always is getting over here. Always is getting over here, and we have used it outside your always, so it's okay to use your assign. Okay, assign clock underscore 2, then first LSB, then we'll be getting divided by 2. If the next bit, it is divided by 4. Finally, if the third bit, then it will be giving you the answer of divided by 60. So this is how it will be going. Okay, now moving ahead. So this is nothing but your main code. The main code is over. Next, we'll be writing a test bench for it. So the test bench is written as stimulus. You already know your clock 2, 4, 8, and 16. What these are, friends? These are nothing but your outputs. So the outputs here are defined in the form of what now? Your wires. Outputs are defined in the form of a wire, and inputs are defined in the form of the resistors. So you can see the resistors, that is, inputs have been defined in the form of the resistors. Finally, the counter divider, what is this? This is the name of the module to which we are writing our test bench. So the name of the module is said to be always same. That is counter underscore divider. This is the name of the module. So the same name must also be used here as well. Finally, some instance name. You can give any instance name, no issues. C1, C2, anything you want. And followed by all your inputs and outputs. You will be writing all the inputs and outputs. As you already know, we will be writing the initial statement for your inputs as well as outputs. So the first initial statement is for your clock. What we have done here in this initial statement, very simple, we have negated your clock. Whatever clock you have, the same clock, we are negating it. And what is the amount of delay we are using? 25 nanoseconds. Similarly, why is this required, friends? The next initial, here in the next initial, we are trying to set your reset. You can observe there, initially the reset is 0. After 800 nanoseconds, the reset will be become equal to 1. You can just observe here, after seconds, the reset is becoming to 1. And plus 200 nanoseconds, that is after 1000 nanoseconds, the execution gets over. So initial, begin and end. So I hope this is clear. Finally, end. Okay, so this is how your whole code is. I hope you know the rest of the steps, which is nothing but you need to go to implementation and implement it. And that is, you need to do the check syntax. After doing the check syntax, you will be coming to the simulation. We will be doing the behavioral check syntax. After behavioral check syntax, you will be doing the simulate behavioral model. So this is what your output will be getting. So this is the output you are getting. Please observe carefully. I'll just try to explain the output. So as you can see here, the first thing, this is my clock. Okay, so it is starting at 25 nanoseconds and it is getting over at what now? 50 nanoseconds, right? That means clock divided by 2 must be what now? It must be twice. You can observe in this diagram here. That is, if it is covering of 2 cycles, 2 cycles in one period, then it should cover off only one pulse. So let us see whether you have got the same output. See, 2 cycles, then you should be covering it with only one pulse, right? We are covering it only one pulse. So this is done. Clock divided by 2 is done. That means if it is 25 nanoseconds to 50 nanoseconds, the next, if you observe clock divided by 2, this one, then you can see it is starting at 25 nanoseconds and it is getting over at 75 nanoseconds. That is, it is twice. Whatever the clock you have here, it has become twice. Okay. Next, come to clock 4. Come to clock 4. If you come to clock 4, you can observe it is starting at 75 nanoseconds and it is getting over at where now? 175 nanoseconds. That means what is happening? 25 multiplied by 4. 25 multiplied by 4 is how much now? 100. Right? So it has started at 75. 75 plus 100. That means where it should come? 175. So clock 4 is over. Next, clock 8. That means what now? 25 multiplied by 8 times. So it has started at where now? 170. 400. So that means it is starting at 375. 375 plus 400. So you can observe here, it should go up till 400, which is 775. 375 plus 400 is 775. So this is how your output is coming. That is, this is how your clock is getting divided. Thereby, we are working with the frequency. Okay, we are trying to work with the frequency. Now, once your reset, what is happening with reset in all this case? It is 0. So once your reset becomes high, then what will happen? Irrespective of your clock, whatever is there, your output has become 0. You can see the output has become 0. And you already know we had written it up till 800 nanoseconds plus 200. Up till where then? Up till 1000 nanoseconds. You can see here up till 1000 nanoseconds. So it is exactly working as per our requirements. So this is your divide clock experiment, friends. Please go through it once again. If you have any doubts, you can just come and ask. Thank you.